Okay, in this video, we are going to look at a question. We are going to go as far back as 1995, paper 1B, KCSE Physics. At that time, they used to have 1A and 1B. Nowadays, we have paper 1, paper 2, and paper 3. However, physics does not change. It just remains the same. So let's go to this question. By then it was paper number 4C. Now I've just called it question 1 because it is in a topic that we have studied before, and this is uniform circular motion. Now let's read the question together. Explain why a pail of water can be swung in a vertical circle without the water pouring out. And over here, I have a simple simulation showing you how that happens. The water does not pour out. We want to explain why, to give a reason why the water does not pour out. So I will take you through the conditions that must be fulfilled for the water not to pour out of the bucket when the bucket is upside down at the topmost point of the swing. So let's pause the simulation so that we can be able to look at the 3 important positions for this bucket. These are the positions that I'd like us to consider. I'm going to name the positions: position A, position B, and position C. It is this position that we are interested with. The blue coloring over here is the water which is in the bucket. Remember, it is the water which is moving in a circular path. Of course, the bucket is also doing the same, but it is the water which can pour out. So we are going to consider this water here as if it was a rigid object of mass m. What are the forces which are acting on it? One of the forces acting on it is its own weight, which is mg. The other one is the force that the bottom part of the bucket exerts on it. Of course, in that position, that force is vertically downwards, and we are going to call that force normal reaction, R. In this position, the normal reaction will be upwards. In this position, the normal reaction will be horizontal to the right, and here it will be horizontal to the left. So these are the 2 forces which are acting on that water. When an object moves in a circular path, something must provide centripetal force for it. What is centripetal force? The resultant force acting on an object which makes that object to move in a circular path. And this resultant force is always pointing towards the center of the circular path. So which forces here are pointing towards the center of the circular path? Both R and mg. So we are going to say that the centripetal force is provided by the value of mg, that is the weight of the water, and the value of the normal reaction. Those are the 2 forces which are providing the centripetal force. And remember, the centripetal force is a resultant force. So that centripetal force is actually mv squared over r. Actually, I should have written it on this other side, but it's just alright. If the water were to pour out at that particular point, if the water were to pour out, then the value of R will be equal to 0. So for the water to pour out, the value of R must be something higher than 0. Therefore, R must be greater than 0. And what is R? At this point, I'm going to make R to be the subject of that expression. R is equal to mv squared over R minus mg. If I make R to be the subject here, I just move mg to the other side of the equal sign, and this is what I get. Now when it comes to this condition, you see this r here, I'm going to replace it with this expression. So I'm going to say mv squared over r, which is the centripetal force, minus mg. Remember, all that represents r, and r is greater than 0. It is at this point that I can say that mv squared over r is greater than, if I move minus mg to the other side of the inequality sign, I'm going to get mg over there. At this point, I'm able to say that the condition for this water not to pour out is that the centripetal force must be greater than the weight of the water. But I can go ahead and cancel this m and this m so that I can get the expression v squared over r is greater than g. What is v squared over r? V squared over r is centripetal acceleration. So I can say the acceleration with a small c down there, centripetal acceleration must be greater than the acceleration due to gravity. And the acceleration due to gravity is actually equal to 9.81 meters per second squared along the equator. So I can say that the acceleration that the centripetal acceleration must be greater than 9.81 meters per second squared. Over here, this m represents meters, but these other m's were representing the mass of the water. So this is the condition that must be fulfilled for the water not to pour out. Again, I can go to the same equation, this one here, and make v to be the subject of that expression. How do I do that? I multiply both sides by r, which means this side becomes rg, and then I find the square root, both sides, and I'm going to find this expression here. And I'm going to say that the speed with which we must swing this bucket, the speed along the circumference, must be greater than a value which is given by the square root of rg, where r is the radius of the circular path. Notice that over here, this speed is independent of the mass of the water in the bucket. So it will work for any quantity of water in the bucket. So these are the three conditions that must be fulfilled. Of course, they are the same condition. It's only that we are reducing them finer to a final level whereby we can get one final condition here, which is independent of the mass of the water in the bucket, which is this one here. But any one of these, if you state any one of these three, you will be in the right direction to answering that question. Of course, remember, we have to explain why. We have not been asked to state the conditions. It's only that I'm stating the conditions so that when it comes to the why, now I can use those conditions, and I'll show you how we go about that. But first of all, remember, you can state any one of these. You can state the condition that must be fulfilled for the water not to pour out is that the centripetal force must be greater than the weight of the water in the bucket. And you will be correct. Or you can say that the acceleration, the centripetal acceleration, must be greater than the value of the acceleration due to gravity, which is 9.81 meters per second squared along the equator. Or you can say that the speed with which we must swing this bucket along the circumference must be greater than a value which is given by the square root of rg. You can see any one of those stated correctly will be the correct answer to a question which asks you to state the conditions that must be fulfilled for the water not to pour out. Now let's go to explaining why. You see, this question reads why because it assumes you know that if you put some water in the bucket, you swing it with a certain speed in a vertical circle, that water will not pour out. It assumes you know that. Now it is asking you why, to explain why the water does not pour out. And you can answer it like this. You can say that the reason why the water does not pour out is because we ensure that the speed with which we swing the bucket is greater than a certain critical speed, which is given by the square root of Rg. This is the critical speed. It is the speed below which the water will pour out and above which the water will not pour out. So it is some kind of a critical speed. So the water does not pour out because we ensure that the speed with which we swing the bucket is greater than a value given by the square root of Rg. Or you can say this: we ensure that the centripetal acceleration is higher than 9.81 meters per second squared. Or you can say it is higher than the acceleration due to gravity. Or you can say that we ensure that the centripetal force is greater than the weight of the water in the bucket. And you will get those 3 marks after giving such an explanation. So I've given you detailed information so that you can be able to know how to tackle this question should the examiner decide to twist it in any way, because that is how the examiners usually approach this question. They look at questions that they've given before and then they want to test. You know, they know that you've done this in school or during practice. You know the answer to this particular question. But in order to test whether you can be able to apply the knowledge which you have, they just twist it a little bit. For example, if you are asked to state the conditions, after studying a question like this one, it will not be difficult because you have done a lot around that particular question. You've not confined yourself to the specific answer of the question. You have looked around that particular question, just in case the examiner asks you anything to do with some of those situations. Elsewhere in this channel, I've dealt with this particular situation in great details because I've looked at all the 3 positions, A, B, C, D, and even shown you how the tension in this rope will change with position or with time. So I'd like you to look at that video. If you click on that card above this video, you'll be taken direct to that video where I've dealt with this situation extensively. Now let's look at question part 2, where we're given that a car of mass 1200 kg is moving with a velocity of 25 meters per second around a flat bend of radius 150 meters. That is, the road is flat. You know, there are some roads which are inclined, especially at the corners. We say that such a road has been banked. This one is flat. Determine the minimum frictional force between the tires and the road that will prevent the car from sliding off. So over here, we've been given the speed of the car, and therefore we have to determine that minimum friction force which will prevent the car from sliding off. Now, what would happen if such a speed has not been attained? If that condition is not attained, let's look at this simulation here that I've created. That is exactly what would happen. In other words, in this diagram, we are looking at a situation where the car is coming towards us. The car is coming towards us, but the road is such that it moves like this. Okay, so we are in such a position that we are looking at it at a particular instant of time when it's coming towards us and taking a curve in this direction. So this is the circular path that it's going to follow. This path like this. So the center of that circular path is somewhere around here. So if that friction force is not sufficient, that car will have to skid off the road. That is usually what happens, and that is what this simulation is showing. You can see that if that condition is not fulfilled, the car will skid off the road. So you need to imagine that. The reason why you need to imagine that is because you need to understand the forces which are acting on this car. I've given a few arrows here. One of them is the weight of the car, which is mg. Then there is the normal reaction on the car due to the road surface, another normal reaction. We are going to just use one of them. Then there is sideways frictional force on this tire and on this tire too. Again, we are just going to use one value. Friction force is usually given by mu r. This is the maximum frictional force that can exist between two solid surfaces. Like for example, the surface of the tire and the surface of the road. This is the coefficient of friction of the road, and this is the normal reaction, which is, in this case, is equal to the weight of the car. This value is usually fixed. This friction force is usually fixed because for any two types of surfaces, the value of mu will be constant. So, but depending on the way the car is moving, that value can be less than this, or take a maximum value, or even be equal to 0, depending on the conditions. This is the normal situation. Around bends or corners, there is usually a speed which the car should not exceed. There is usually a speed limit, because if it exceeds that speed, then the car is likely to skid off the road or to slide off the road, because that is the term that they're using here. The car is likely to slide off the road if the speed is above that critical speed. Now, how do we get that critical speed? We have to think about the centripetal force all the time. Centripetal force, because this one is an object which is moving in a circular path. The centripetal force must always be less than the maximum frictional force between the tire and the road surface. That is the condition for the car not to slide off the road around corners. And of course, we can say that the centripetal force is this one here, must be less than this friction force, must be less than that maximum frictional force, mu r. And given that the value of r is equal to mg, we can say that mv squared over r must be less than mu mg. And at this point, even at this point, we can say that for the car not to skid off the road or to slide off the road, the centripetal force must be less than the maximum friction force between the tire and the surface of the road. And when we substitute for r and we have these values cancelling out, we can see that v squared over r, which is actually is equal to centripetal acceleration, must be less than a value given by mu g. Again, this is the coefficient of friction, and this is the value of the gravitational field strength. Let's go right ahead and we make v to be the subject of that equation, and we can see we can have r mu g, and we have square root. Of course, there is an inequality here. Don't forget that. The speed with which the car moves around that particular bend must not exceed, it must not be higher than a value which is given by the square root of r mu g, where r is the radius of that circular bend, mu is the coefficient of friction, and g is the gravitational field strength. So just like in the previous question where we were looking at the conditions that must be fulfilled for the water not to pour out of this bucket at the maximum point, these are the conditions that must be fulfilled for this car not to skid off the road around that bend. We are assuming, of course not we are assuming, we know that since it is a flat bend, the centripetal force is provided by the sideways frictional force, which is given by mu r. And we are saying the friction force, usually the friction force between any two surfaces can be equal to 0 or greater than 0, but it must be less than or equal to a value given by mu r. This is a very important condition. For any two surfaces, this is the way it works. This is the maximum friction force between the two surfaces. Of course, 0 friction force. Why am I saying 0? This is an object on a surface such as this one. And let's say we are pulling this object, it's some kind of a heavy box on a rough surface. So we are pulling it in this direction. What are the forces which are acting on this box? One of them is its own weight, mg. The other one is normal reaction. And the last one, let me just change color there so that I can say it is here. Between the two surfaces, there is frictional force. This friction force can be 0. How? If we don't apply a force, a horizontal force on the box, the friction force will be 0. If we apply a small amount of force, but the box does not move, it means that the friction force has taken a value, but that value is still less than the maximum frictional force that can act between the two surfaces. If we continue to increase the pull, the friction force continue to increase. So we can look at the way the friction force increases with this force. For example, it is this force that we are increasing. We are increasing that force, and this is the friction force. At any one point, the amount of force that you apply on that object will be equal to the friction force. But a point will come whereby if you continue to apply this force, the friction force will not increase. It will have reached its maximum value here, which is given by this. So definitely you can see that the friction force obeys this inequality in the sense that it can be equal to 0 or greater than 0, but it must be less than or equal to mu r. So we are saying that when a car moves around this circular bend here, all the centripetal force is provided by the frictional force between the tire and the road surface. And we can see that the centripetal force increases with the speed of the car. So you can be able to see that if we are not very careful, the centripetal force can reach a value whereby it is greater than the value of mu r. In other words, we will say that the frictional force is not sufficient to provide the required centripetal force. Let me repeat that because it's very important. The frictional force is not sufficient to provide the required centripetal force. In such a case, this car is just going to skid. And why does it skid? Is because the car is moving with a speed which is very, very high, making it impossible for that centripetal force to be provided by the only agent which is responsible for providing that centripetal force, which happens to be frictional force. So around corners, there must be a speed limit which motorists must not exceed. If they exceed that, then the car is going to slide off the road into the ditch or something like that. Those are the conditions that must be fulfilled. Now that I've given you the theory into this question, we are asked to determine the minimum frictional force between the tires and the road that will prevent the car from sliding. That minimum frictional force is mu r, and it will be equal to mv squared over r. So we can say that F centripetal is going to be equal to mv squared over r, and we substitute here, we are going to get the value of m is 1200, v squared is 25 squared divided by 150, and this is what gives us 5,000 newtons. So in order to answer the question, determine the minimum frictional force. This is the minimum frictional force between the tires and the road, which is just sufficient to prevent the car from sliding. Otherwise, if the speed is such that it is higher than 25, that centripetal force will be higher than 5,000. And you know, the friction force cannot increase above this value. This is the maximum frictional force that the surface can offer on the tire, and therefore the minimum frictional force between the tires and the road must be 5,000. And that is how you answer this question. Now remember to go through the video that I've already mentioned so that you can be able to understand the theory behind all these situations, because a clever way of revising is to be able to understand the concept which the examiner was testing, understand it so thoroughly in such a way that if the examiner were to twist it in a different way, you will still be within safe boundaries, because you will quickly be able to understand what the examiner wants. But if you do your revision in such a way that you just want the exact answer to this particular question, and you don't, look around that particular question to see what is possible for the examiner to twist, then you will be doing yourself a disadvantage, because you will end up doing so many questions, but as soon as the examiner twists one of them, it catches you off balance and you find yourself failing that particular question. And that is how you would have answered this question if you were the one sitting for this examination.